Hi, I'm Mark Barsamian. In this video, I'll be discussing local extrema and the first derivative test. This material is from section 4.1 of the book. The corresponding homework is this collection of 6 exercises from section 4.1. We'll be using some useful concepts that were discussed in the previous 3 videos, concepts from section 4.1. This correspondence between the sign behavior of f prime at a particular x value and behavior of the graph of f of x at the same x value. The idea that if f prime at c is a positive number, then that means that the line that's tangent to the graph of f at x equals c tilts upward. And the correspondence between the sign behavior of f prime on a whole interval and the behavior of the graph of f on the whole interval. The idea is that if f prime is known to be positive on a whole interval, then f of x is going to be increasing on that whole interval. We introduced the notion of a partition number for f prime. A partition number for f prime of x is a number x equals c, so it's an x value that has the property that either f prime parentheses c is 0 or f prime parentheses c does not exist. And we discussed critical numbers. A critical number for a function is a number that has 2 properties. The number is a partition number for f prime, and the number is in the domain of f. So in other words, a critical number is an x value that has these 2 properties. Either f prime parentheses c is 0 or f prime parentheses c does not exist, and f of c does exist. So I want to start by discussing local extrema. When a graph of a function is available, it's easy to notice high and low points on it. So for instance, here's a low point on the graph, here's a high point, here's a low point, here's a high point. We call the y-coordinates of such a point a local max or a local min. The definitions follow on the next page. A local maximum for a function is a y value, y equals f parentheses c. So in other words, it's a y value on the graph of that function that has this property. The function has to be continuous on an interval containing that x value, and that y value has to be the greatest y value on that interval. In other words, if you compare that y value to all other y values for x's in that interval, the y value f parentheses c is greater than or equal to all others. Similarly, for the definition of local min, the y value is the least y value on the interval. So f parentheses c is less than or equal to f of x for all x in the interval. So that's the idea of a local maximum and a local minimum. Collectively, we say a local extremum is a y value that's either a local max or a local min. When a function is given by a formula, not by a graph, it's natural to wonder if there's some way to scrutinize the formula and determine the local extrema. And it turns out there is a way. The key is to notice something about the sample graph shown earlier. The high points and low points, high and low, always occur at points on the graph of f that have either a horizontal tangent line or no tangent line, because there is a cusp on the graph. So let's go back up and look at that graph. Here's a low point and a high point. Those both have horizontal tangent lines. Here's a low point and a high point. Those points in the graph don't have tangent lines because they're sharp points, but they're still local extrema. This is the lowest point in the vicinity. This is the highest point in the vicinity. So their y-coordinates are local mins and local maxes. So in other words, we have this theorem about local extrema in critical numbers. If f of c is a local extremum, remember that means that f of c is a y value that's either the greatest or the least y value nearby, then the x value, x equals c, is a critical number of f. Now remember what that means. A critical number for f of x is an x value where f of c exists, so there is a y value on the graph, and f parentheses c equals 0, or f parentheses c does not exist. So that would mean that the tangent line is horizontal, or either there's not a tangent line or the tangent line is vertical. So this local min occurs at this x value c subscript 2. That's a critical number for the function because that's a place where the y value does exist and the tangent line is horizontal. This local max occurs at x equals c subscript 3. That x value is a critical number because the y value does exist and the tangent line is horizontal, so the derivative is 0. This local min occurs at c subscript 4. C subscript 4 is a critical number because the y value does exist and the derivative does not exist because there's no tangent line at that point. This local max occurs at c subscript 6. That number, c subscript 6, is a critical number because the y value does exist, but the derivative does not exist because there's no tangent line there. So this theorem 2 about local extrema and critical numbers makes sense from what we've seen from the graph. The only place where a local extremum for a function can occur is at an x value that's a critical number for the function. Furthermore, notice that not all critical numbers for f of x correspond to points in the graph that have a local max or min. Let's go back up and look. This is a critical number, c subscript 1, because it's a place where the y value does exist and the tangent line has slope m equals 0. So that means that the derivative is 0. But that's not a max or a min. Here's another place that's a critical number. This number c subscript 5 is a critical number because the y value does exist and the tangent line has slope m equals 0. But that point on the graph has neither a max nor a min. Same thing for this critical number. The y value does exist. The derivative does not exist because there's no tangent. But you can see that there's neither a max nor a min at that point. Now, notice the places where there are extrema, such as this one, the graph changes from going down to going up. This place, the graph changes from going up or going down. So for a critical number, for an x value to be a location where there's a max or a min, the x value has to be a critical number and the function has to change from increasing to decreasing or change from decreasing to increasing at that x value. So that's this observation here. F of x must change from increasing to decreasing at that x value or from decreasing to increasing. So that's the essence of what's called the first derivative test. Remember, this discussion started with this question: is there some way to scrutinize the formula for f of x and determine the local extrema? Again, they're easy to spot on a graph, but what if you just have a formula for f of x? Is there a test you can do, some way of scrutinizing the formula for f of x to determine the local extrema? Well, here's the first derivative test. If you have a critical number for a function, that means, again, that number x equals c is in the domain, so f of c is defined, and either f prime parentheses c is 0 or f prime parentheses c is not defined, so that's what it means for x equals c to be a critical number. Construct a sign chart for f prime in the vicinity of x equals c. And if the sign chart has this signature, f prime changes from negative to positive, that means that f changes from decreasing to increasing at x equals c. So that means that f parentheses c would be a local min. On the other hand, if f prime of x has this signature, that is, f prime changes from positive to negative at x equals c, then that means that f would change from increasing to decreasing. So that means that the y value, f parentheses c, would be a local max. On the other hand, if f prime has this signature, f prime is positive to the left of c and positive again to the right of c, that means that f of x is increasing to the left of c and increasing again to the right of c. Then that would mean that there is neither a local max nor a local min at x equals c. Let's go back up and look at our graph. That's this kind of place. F of x is increasing to the left of c5, increasing again after c5. So there is no max or min at x equals c subscript 5. And similarly, if the first derivative has this signature, the first derivative is negative to the left of c and negative again to the right of c, that means f of x is decreasing to the left of c and decreasing again to the right of x equals c, then again, in that case, there is neither a local max nor a local min at x equals c. So with that in mind, let's look at some sample graphs. Notice this function has a local min at x equals c because there is a horizontal tangent. So the first derivative is 0 right at that point. And the graph is decreasing to the left of x equals c. The graph of f of x is increasing to the right of x equals c. So that means the first derivative has this signature. The first derivative is negative to the left of x equals c. The first derivative is 0 at x equals c. And the first derivative is positive to the right of x equals c. So that is tells us that at x equals c, there's a local min. So the y value is the local min. F parentheses c is the y value, and that's a local min. So that's an example of this kind of signature, this kind of result from using the first derivative test. Let's look at some examples where the first derivative is not defined, but the y value is defined. So, for instance, this point on the graph, there is a y value, so f parentheses c is defined, but there is no tangent line, so f parentheses c is not defined. Now notice that to the left of x equals c, the derivative is positive because the function is increasing, or corresponding to the fact that the function is increasing. To the right of x equals c, the first derivative is negative. That corresponds to the fact that the function f of x is decreasing. Right at x equals c, the first derivative is not defined. Well, that's one of the signatures that is described in the first derivative test. That's this. Doesn't matter what's happening at x equals c, as long as it's a critical number, whether or not there's a y value, whether or not whether f prime is equal to 0 or f prime is not defined. Either way, if the derivative has this signature at x equals c, then x equals c is going to be a local max. So there is a local max at that location, and the y value of the max is what's called the local max. So f parentheses c is a local max. Now look at an example where there is neither. Look at this graph. Notice that the derivative does not exist at x equals c. There is a tangent line at x equals c, but its slope is undefined. So the derivative does not exist at x equals c, but the y value does exist because there is a point on the graph. So that x equals c is a critical number. Now notice that to the left of x equals c, the derivative is positive. That corresponds to the fact that the function is increasing. And to the right of x equals c, the derivative is positive again because the function, or corresponding to the fact the function is increasing. And you can see that that's one of these signatures where the first derivative test tells us there's neither a local max nor a local min. Sure enough, there's neither a local max nor a local min. Let's go on. Example 1 is similar to one of your homework problems. A function f of x is known to be continuous for all real numbers, and its sign chart for f prime is shown below. So the question is, find the x-coordinates of all local extrema of f of x. Well, the first thing to do here is to remember Theorem 2. Theorem 2 says the only place where a local extrema can occur is at an x value that is a critical number for the function. Now remember what critical numbers are. They're x values where the y value does exist and the derivative is 0 or the derivative does not exist. So those are the x values that we have to look for, because those are the places where local extrema can exist. Well, note that we're told that f is continuous for all real numbers. So this criterion that f parentheses c must exist, well, that's taking care of f of x exists for all real numbers, because that's part of the criterion for f of x to be continuous. So this first statement is always true because f of x is continuous for all real numbers. But it's this second criterion that we have to think about. The only critical numbers are the places where f prime equals 0 or f prime parentheses c does not exist. That's these four x values. So those are the only locations where there could be extrema. So now we have to go back and look at the first derivative test. First derivative test says that the only place there's a local min or a local max is at the places where the derivative changes sign. These other places where the derivative does not change sign, there is no local max or local min. So we don't care about those places. So we should look for places that have this signature where the first derivative changes sign. So we see there's no local max at x equals a because the derivative does not change sign, and there's no local max at x equals c because the derivative does not change sign. But there is a local min at x equals b. And we can explain why by saying it's because f prime changes from negative to positive. And we can see there's a local max at x equals d because f prime changes from positive to negative. I might have said the wrong thing. F prime changes from positive to negative there. Let's go on. Example 2 is similar to a bunch of homework problems. We're going to revisit the function from example 2 in the video from homework 54. This function f of x equals minus x to the fourth plus 4x cubed. And the question is to find the local extrema of f of x. All right, well, I'm not going to go through all the details because we went through them in that video. I'll just give the highlights. So there's our result from the earlier video. We found the derivative for f of x, and we factored it, and we found the critical numbers where x equals 0 and x equals 3. We made this sign chart for f prime, and we used that sign chart to tell us where f was increasing and where f was decreasing. Maybe I'll also add what happens at those critical numbers. Now, let's look at this in light of the question. The question was find the local extrema. Well, from the first derivative test, we know that the local extrema can only occur at the critical numbers, and they can only occur at critical numbers where the derivative changes sign. That's only this critical number. F prime changes from positive to negative there. there is not a local extremum at that critical number because f prime does not change sign there. Now, the question was to find the local extrema. The local extrema is not the number x equals 3. The local extremum is the y value, so we have to find the y value to find the local max. So we have to substitute x equals 3 into the formula for f of x. So the local max is this number, y equals 27. Now, in the book, in the MyLab exercises, they want you to answer in the following way. So notice what this is doing. This is acknowledging that the local max is this y value. F parentheses 3 is that y value. But in wanting you to answer this way, to build a little equation like this, not only are you saying that you know what the y value is at for the local max, you also know the x value where it occurs. So this equation does two things. It gives the y value, that's the value of the local max, and it gives the x value where that local max occurs. Let's go on. We're supposed to illustrate this on the given graph of f of x. Well, look what we found on the sign chart. At x equals 0, there is a horizontal tangent, but not a local max. At x equals 3, there is a horizontal tangent that is a local max, and we know the x, y coordinates of that local max. So let's put all this stuff on the graph, both of those things. So there are the coordinates of that point, 3, 27, and the fact that it's a horizontal tangent there, and also at this other point that is not a local max or local min. That's the end of that example. Let's go on. Example 3. This is similar to one of your homework problems. F of x is this function. Find the critical numbers of f of x. Well, notice that, first of all, f of x is a continuous function. So the y values exist at every x value. So the critical numbers are going to be places where f prime is equal to 0 or f prime does not exist. So we have to find f prime of x. The key thing here is to remember, this is kind of a blast from the past. This is a product, so we need the product rule. So the product rule says that. Let's do the derivatives in the next step. Start by copying down all the stuff that's not going to change. Now the derivative of x minus 2 is going to be 1 minus 0. The derivative of e to the 3x is going to be 3 times e to the 3x, using exponential function rule number 2. Remember that rule. The derivative of e to the kx is k e to the kx. All right, let's clean this up. Now notice I did a strange thing. I left this e to the 3x here sitting next to this 1. Why didn't I just get rid of that 1? Well, the reason is I noticed that over here on the right we also have an e to the 3x, and it's sitting next to this term, 3x minus 6. I got that by distributing this 3 to those two terms. Written that way, the way I have this written here, it's clear that we should factor out e to the 3x. So I factored that term out. Now let's clean this up some more. Now we have to find the x values where f prime is 0 or f prime does not exist. Let's do that on the next page. Let's first address the issue of the x values where f prime does not exist. notice that this f prime of x is continuous, so it is always defined. There are no bad x values. So we have to look for x values that cause f prime to be 0. Now, we have done this before, this kind of solving of an equation. The key thing is to notice that this is a product of two things and the product equals 0. Remember the zero product property. A product, A times B, equals 0 only when A equals 0 or B equals 0. So that's one thing to remember. The other thing to notice is that this thing can never be 0. In fact, we can say that that thing in the circle, e to the 3x, is always positive. And it's because e raised to any power is always greater than 0. Remember, the exponential function graph has this shape. Now, our function is not e to the x, it's e to the 3x. But the thing is, this graph should remind you that no matter what you put in the exponent, you always get a y value that's greater than 0. So look, we have a product of two things, a left thing and a right thing, and the product has to equal 0. So that means that the thing on the left has to be the thing that's 0. So let's solve that equation for x. That's the solution to that equation. That's the only x value that causes f prime to be 0. And so that's our critical number for the function f of x. So that's the answer to question A. Question A was to find the critical numbers of the function. Let's go on. Question B, find the intervals on which f of x is increasing and the intervals on which f of x is decreasing. Well, the solution strategy should be this. Find f prime, make a sign chart for f prime, and use the sign chart for f prime to answer these questions. Well, we've already got f prime, so we just need to make a sign chart for f prime and use that sign chart for f prime to answer these questions about f. Now, why is that our strategy? Well, let's go back to what we reviewed at the very beginning of the video. This correspondence between the sign behavior of f prime and the increasing, decreasing behavior of f of x. We're supposed to find, in our current example, the intervals where f of x is increasing or decreasing. So we'll answer that question by studying the sign of f prime. So that's why we have this strategy. Okay, so remember how to make a sign chart for f prime. We start by making a number line and putting the partition numbers for f prime on the number line. Now the first thing I'm going to do is label a sign chart though, and I'm going to put the formula for f prime to remind us of the function we're dealing with. So there's our sign chart so far. We put the only partition number for f prime on the number line. It was this x equals 5/3 because that causes f prime to be 0. And then now we have to find test numbers. Let's just use some simple ones, x equals 0 and x equals 2. So there are my sign calculations. Now the key thing to notice here is that I didn't actually find values for these expressions. All I cared about was whether they were positive or negative. Well, they're always positive because remember, e to anything is always positive. So that makes my sign calculations actually quite simple. All I had to do was figure out the signs for these expressions on the left. Now let's put that information on the sign chart. So there's a sign chart for f prime finished, and we can use that now to answer the questions about f of x. So there we go. F is decreasing on this interval, and we say why? It's because f prime is negative. F is increasing on this interval because f prime is positive. Again, notice my use of nouns. I don't say it's increasing because it's positive. That would be incorrect. We say that f is increasing because f prime is positive. Question D, find the local extrema. Well, let's go back up and remember the first derivative test. Local extrema can only occur at critical numbers where the first derivative changes sign. Well, look, we only have one critical number. It's this one, x equals 5/3, and at that critical number, f prime changes sign from negative to positive. So we see that there is a local min at x equals 5/3, and it's because f prime changes from negative to 0 to positive there. Now the question, though, was not to find where the extrema occur, but to actually find the extrema. So we have to find the value of that min. We have to find the y value. So it's denoted by this symbol, f parentheses 5/3. Now for that I have to substitute 5/3 into the original function, f of x. Now remember what that is. The original function was this, parentheses x minus 2 times e to the 3x. So we review the form of the function, and then it's useful to have the empty version in order to do our calculation. So there's our final answer. The local min is this y value, but we present it in this equation to make it clear that that y value is the min, and this x value is the x value where it occurs. Let's go on. Illustrate that on this given graph of f of x. Well, we just found that the local min has that y value. That's about negative 49. And that occurs at x equals 5/3. So we'll illustrate that on the graph by drawing a horizontal tangent here and putting the coordinates of this point on the graph. Notice the y coordinate of that point is close to negative 50. The x coordinate is 5/3. There's an illustration. Let's go on. Example 4. Let's revisit this example we did in the video for homework 53. In that video, we were given this graph of f prime, and we were asked to find the intervals where f was increasing and the intervals where f was decreasing, and we were asked to sketch a possible graph of f of x. What's new in this question today is I want to find the x-coordinates of the local extrema for f of x. All right, well, start by remembering how we answered questions A and C. We filled up this table. We made observations about the sign of f prime, and we translated them into conclusions about the behavior of the function f of x. So our observations were that at x equals negative 3 and at x equals 4, f prime was equal to 0. And that corresponded to horizontal tangent lines on the graph of f. And then we noticed that on this interval and on this interval, f prime is positive. That corresponds to f being increasing. But on this interval, f prime is below the axis. F prime is negative. So that's how we answered the questions about f being increasing and decreasing, and we made a graph as well. You can look back at that video to remember how that graph looks. Now our current questions are, our current question is to find the local extrema. So let's go back up and look at the first derivative test again. The first derivative test says that local extrema can only occur at x values that are critical numbers and where the derivative changes sign. Well, let's go back and look at our information about the derivative and see where the derivative changes sign. Here we have two critical numbers, but the derivative does not change sign at this first critical number. The derivative went from positive to 0 and back to positive. So there's a horizontal tangent at x equals -3, but not a max, not a min. But look at x equals 4. To the left of x equals 4, f prime is positive. To the right of x equals 4, f prime is negative. That tells us that at x equals 4, there is a local max. Let's go back up and look at the graph of f prime. At x equals 4, f prime changes from being above the axis to being at x-intercept and then being below the axis. So this x-intercept on the graph of f prime corresponds to a local max on the graph of f. F prime changes from positive to 0 to negative. That tells us that the graph of f of x will be changing from increasing to horizontal to decreasing. All right, let's go on. Example 5. F of x is this function, 3x plus 75 over x. Find the critical numbers of f of x. All right, well, let's start by finding f prime of x. Now, to find f prime of x, it's useful to first rewrite f of x. We were given f of x in positive exponent form. It's useful to write it in power function form for the purpose of finding the derivative. So there's our derivative calculation. Notice the first thing we used was the constant multiple rule. Then we used the power rule. That was why it was useful to have the function in power function form. The result of that is an expression that is in power function form. But once we have the derivative, it's useful for future stuff to convert that derivative to positive exponent form. So there's our derivative. So we have the derivative. Now we have to find the critical numbers for f of x. Let's do that on the next page. Now remember what critical numbers for f of x are. They're x values that are partition numbers for f prime and x values that are also in the domain of f of x. So let's start by finding the partition numbers for f prime. We'll notice right away that when x is 0, f prime of x does not exist because of that thing. So x equals 0 is a partition number for f prime. Are there any other partition numbers? Well, let's set f prime of x equal to 0 and solve for x. So we see that the solutions to this equation, f prime equals 0, are the numbers x equals 5 and x equals -5. So our conclusion is that the partition numbers for f prime are the following three numbers. Those are the partition numbers for f prime. But remember, the question was to find the critical numbers for f of x. So to be a critical number for f of x, the x value has to be a partition number for f prime, but also has to be in the domain of the original function. Well, remember the original function. Let's test our three partition numbers for f prime and see if they're in the domain of f of x. We see that f of x does exist when x is -5, it's the number -30, and when x is 5, it's the number +30. But f parentheses 0 does not exist. So of those three partition numbers for f prime, the only numbers that qualify to be called critical numbers for f of x are x equals -5, x equals 5. So that's the answer to our question. Our question was to find the critical numbers for f of x. Let's go on. Question B, find the intervals on which f is increasing and the intervals on which f is decreasing. Well, our solution strategy should be this. Make a sign chart for f prime and use the sign chart for f prime to answer the questions about f. So to make a sign chart for f prime, we start by labeling it. And we put all the partition numbers for f prime on the number line. And remember, the way that I do my sign charts is that I also put the behavior of f prime at those partition numbers. So let's find some test numbers. Now I'm going to pick test numbers on the outside of these partition numbers that are very far out. You'll see why in a minute. Otherwise, I'm going to pick test numbers that are just 1 unit away from x equals 0. So let's find the sign of f prime at those test numbers. Now you see why I chose these test numbers so far away. It's because when I do this calculation, it was convenient to have a number that was so clearly smaller than 3 that I knew that the result was just going to be positive. So there are my signs. Let's put that sign information on the sign chart. Now we can answer our questions about where f is increasing or decreasing. I'm going to shrink this stuff so that I have room. So there's our conclusion. F of x is increasing on these two intervals because f prime is positive. Remember that I state that in a sentence and I say why and I use the noun. F of x is what's increasing, f prime is the thing that's positive. And f of x is decreasing on the intervals -5 to 0 and 0 to 5 because f prime is negative there. Let's go on. Question D, find the local extrema. Okay, well let's go back up and look at our sign chart. The local extrema have to occur at critical numbers. There are only two critical numbers, x equals -5 and x equals 5. So we have those two x values that are the only candidates where local extrema can occur. Now notice, at x equals -5, f prime changes from positive to 0 to negative. So that tells us that there's a local max at x equals -5. Whereas over here at x equals 5, f prime changes from negative to 0 to positive. So that tells us there's a local min at x equals 5. So we've determined that there is a local max at x equals -5 and a local min at x equals 5, but our job was to find the local extrema. That doesn't mean just find where they happen. That means to actually give the values of the local extrema. So to do that, we have to find the y values. So the local max is going to be denoted f parentheses -5. And the local min will be denoted f parentheses 5. So we have to get those values. Well, remember, we found those values earlier. When we were testing the partition numbers for f prime to figure out if they qualify to be called critical numbers for f, we computed y values. We found that f parentheses -5 is -30, and f parentheses 5 is +30. So we'll put those y values in down below. So these equations tell us the values of the local max and the local min. The value of the local max is -30, and the equation also tells us where that occurs. Now notice there's something strange here. The local max is lower than the local min. Why can that happen? It doesn't seem right. Well, let's go on. Question E says to illustrate on the given graph of f of x. Well, you see on this given graph, we can see the local max is over here, and the local min is over here. And the reason that you can have that kind of thing happen is that there is this discontinuity in the middle. There's a vertical asymptote. So it's possible to have this chunk of the graph be lower than this chunk of the graph, but this chunk of the graph is the chunk that has a local max, and this chunk of the graph is the chunk that has a local min. All right, let's go on. There's one more problem. In this problem, this is similar to your problem number 97. A drug is administered by a pill, and the drug concentration is described by this function. In this equation, t is the time in hours after the pill was taken, and c parentheses t is the drug concentration at time t in units of milligrams per milliliter. So first question is to find the critical numbers for c of t. So we start by finding c prime of t. So the result is c prime parentheses t is this expression. I used the quotient rule. I'm not going to go through the details here because it takes quite a while, but it's standard quotient rule. Now here we're only really interested in t greater than or equal to 0. And so there's c prime of t. Now we're supposed to find the critical numbers for c of t. Well, we start by finding the partition numbers for c prime. Now we first ask, are there any values of t that cause c prime to be undefined? And the answer is no, because the denominator will never be 0. So the only partition numbers for c prime are the numbers that will cause the numerator to be 0. And those are x equals 3 and x equals -3. So the only partition numbers for c prime are t equals -3 and t equals 3 because they cause c prime to be 0. Now we have to ask the question, are those critical numbers for c? Well, the question is, does c exist at those times? Well, c always exists because it's a rational function and the denominator will never be 0. And so because c prime is 0 and c exists, we know that both of those t values are critical numbers. All right, let's go on. Find the intervals where c is increasing and the intervals where c is decreasing. So our strategy is make a sign chart for C prime, well, we know how to do that. We label the sign chart. We put the partition numbers for C prime on the sign chart. We put the behavior at those partition numbers. Then we choose test numbers. I'm not going to go through the details of the sign calculations. It's a standard thing to put these test numbers into this formula for C prime. The result is that C prime is negative out here. C prime is positive here. C prime is negative here. And so that tells us the following information about C. So we see that C is increasing on this interval because C prime is positive. And we see that C is decreasing on these intervals because C prime is negative. Now, the thing is, we're talking about a concentration function, so we're not really interested in this function as an abstract mathematical function. We're only really interested in the function for t greater than or equal to 0. So really, that's the chunk of this sign chart that we're interested in. All right, let's go on. Find the local extrema. Well, I'm just going to do the local extremum at t equals 3. So we only care about this local max at t equals 3. So we have to find the local max. That means we have to plug t equals 3 into the formula for c of t. So the result is that c parentheses 3 is the local max. So in other words, it's this y value, 0.69 over 18, which is about 0.038. And we write this equation, c parentheses 3 equals 0.69 over 18. That gives us the value of the local max, and it tells us the value of t where it occurs. There's one more part to this question. Illustrate this result using the given graph of c of t. Well, we found that there's a local max at t equals 3, and we can show the t and the c of t coordinates, roughly 3, 0.038. This y coordinate is about 0.038. And we see that to the left of that max, the graph of c is going up, and to the right, the graph of c is going down. That's the end of this example, and that's the end of the video. Thank you.